About 3.8 billion years ago, many of these icy bodies were whisked away to the Kuiper Belt, a frigid neighborhood just beyond the outermost planet Neptune.
Icy objects in the Kuiper Belt probably formed closer in toward the sun, where the giant planets are. But then gravitational interactions with those giant planets made those icy objects migrate outward.
Our spacecraft navigates through this dark, disk-like region, which is almost 2 billion miles wide and is estimated to hold over 6 billion comets. We eventually touch down on the surface of one of these icy boulders.
Landing on a comet would be a pretty tricky affair. So you could kind of imagine dirty snow that's covered with exhaust. And if you step on it in places, you can punch through to places where there's more fresh material underneath it.
The Kuiper Belt objects appear to have fairly stable orbits, so they won't be that much fun to ride. We lift off in search of a comet that will cut a more exciting path through our solar system. We navigate farther out to a sparsely populated region called the scattered disk, which is home to icy bodies with long elliptical orbits. The slightest disturbance can send these unstable objects careening into the inner solar system, where they become known as short-period comets, those which orbit the sun every 20 to 200 years.
The scattered disk region is thought to be the primary source of the short-period comets. They are kicked into the inner solar system either by interacting with Neptune or possibly passing the stars.
Our spacecraft witnesses Neptune's gravitational influence at work, dislodging a comet out of the scattered disk. This comet would be too dangerous to land on, so we'll track alongside it on its transformational flight through our solar system.
So what would happen if we were on a journey toward the sun? Well, it would start off looking like a dark asteroid. Nothing much is happening. It doesn't have an atmosphere around it.
As you start to travel toward the inner solar system, get up to Jupiter or even closer to the sun, the comet would start to become active.
The warmth from the sun starts to heat up the comet, and all the frozen material that's trapped on the inside starts to convert from ice into gaseous material. And so these gas jets can actually punch through the crust of the comet and form jets. As these jets flow away from the surface, they can start to pull dust and rocks with them. And this forms a kind of hazy atmosphere around the comet's nucleus. We call this the coma.
As it zooms by Earth, the coma of a comet can grow to be larger than the diameter of our sun. Solar radiation eventually pushes this cosmic halo behind the nucleus, forming two bright tails, one of dust and the other of gas.
So there'd be a tail growing and growing and growing, and you would eventually become engulfed in just a really rocky, icy, particle-filled environment. It would be very difficult on your spacecraft because it'd be like flying through a blizzard.
Some tails can stretch for 100 million miles, more than the distance between the sun and the Earth, as it travels towards our home star. It's one of the most spectacular spectacles of our solar system.
Today we're going to see what happens when we take a comet that's been in the cold, dark, icy outer reaches of the solar system, and we're going to send it inward towards its perihelion, or the point of closest approach to the sun. Now, dry ice is frozen carbon dioxide, and this is a very common constituent of comets. Let's see what happens. When we take this piece of dry ice and we drop it into the warm water, the dry ice starts to sublimate. That means it converts directly from a solid frozen state into a gaseous state. And as the water starts to warm up certain parts of the dry ice first, you can start to see that little jets kind of form on it. And this forms a hazy atmosphere called a coma. You can see that the little chips of dry ice are constantly changing as they sublimate away. Sometimes they speed up, sometimes they slow down. So if this was a comet, you can get the idea that as the comet approaches the sun and the volatiles start to vaporize, this can actually change the comet's rotational state and even its orbit.